Great. Yeah, I want to say thanks to the organizers for inviting me to speak today, and thanks everyone for coming. Oh, I forgot to turn it on. Yeah, sorry about that. Um, yeah, so thanks to the organizers, and thanks everyone for coming. I'm really happy to be here. It's been a really great week of talks so far. So, yeah, I want to tell you about a project. It's in progress, joint with Auel and Alena Pirutka, where we study varieties over the rational numbers and look at sort of comparing their rationality to the rationality of their reductions mod p for varying primes p. Okay, so let me start with some recollections on rationality. So I'll let X be a smooth projective variety over a field K. Then we say X is rational over K or K rational if there's dense open subsets U in Pn and V in X, such that U and V are isomorphic actually over that field K. So let me start with a simple example. I'll take this conic x squared plus y squared minus z squared equals 0. And we can see that this is rational via stereographic projection. So I have some point on my conic, and I project away from that point onto a complementary P1. And I can even write this map down explicitly if I sort of pick that point. And in this way, I can parameterize the points on X via rational functions in T. So this is kind of the really nice property of rational varieties. So you can parameterize their points in this way. Okay, but since I'm working over non-algebraically closed fields, there's another related notion, which is being geometrically rational, which is just to say maybe you may or may not be rational over the ground field, but when you base change to the algebraic closure, you become rational. Okay, so if a variety is rational, of course, it's geometrically rational. The converse need not be true. Let me do another example. So if I take a different conic, say x squared plus y squared plus z squared equals 0, and now pick, say, the rational numbers or the real numbers, of course, geometrically, this is isomorphic to the conic that we just looked at, but this has no real points. Right? And in fact, this is not rational over R, but it is geometrically rational. Okay, and how do you show that this is not rational over R? Well, this you can apply this this theorem due to Lang and Nishimura, which says that if a variety is rational, then it has a rational point. So again, over that field. Okay, and we often call this kind of theorem an example of a rationality obstruction, right? Not having rational points obstructs being rational. Okay, so sort of any property of projective space that's preserved under birational equivalence is going to be is something you could use to obstruct rationality. So any of these birational invariants. So maybe let me give some examples. Say over the complex numbers, there's a lot of topological obstructions. So if I start with something rational, then sort of going back to Riemann, global sections of holomorphic P forms has to vanish for P positive. Sayre showed that the fundamental group has to be trivial. Artin and Mumford showed that the third homology group can't have any torsion. So these are all sort of topological properties. But say more generally, there's sort of more maybe arithmetic kind of obstructions like Lang-Nishimura that I just mentioned. There's also sort of more general notions than just rationality, like being stably rational or unirational, and rationality is the strongest, so it implies these others. The Brauer group for smooth projective variety is a birational invariant. So if the variety is rational, it has to have the same Brauer group as that of projective space, which is that of the ground field. And you can also use the birational automorphism group. So for projective space, this is infinite. Okay, so these are just some examples, and the sort of the point is that if you want to show that a variety is not rational, you have to find one of these rationality obstructions. You have to find some invariant for your variety that doesn't match that of projective space. And sort of on the other hand, if you want to show the variety is rational, this can often be difficult. You have to really explicitly write down a rationality construction. Okay, so let me give one more example. Let's take now a quadric surface over a field K. And kind of similar to the examples with the conics that we saw earlier, this quadric is rational if and only if it has a point. The forward direction, again, being Lang-Nishimura, and the reverse direction is, as we saw with the conics, once you have a point, you can project away from that point. like it's an explicit rationality construction. Okay, so I started with project surfaces as an example, and sort of the main object of this talk is going to be quadric surface bundles. So let me do a more complicated example. So I want to think about cubic fourfolds. So I'll take X to be a smooth cubic fourfold. Let's say work over a number field. I'm going to sort of pretty soon restrict myself to working over the rationals. The general expectation is that a general X of this form is going to be geometrically irrational, so even base changing all the way up to the complex numbers. But there's no proof of this fact, I guess it's sort of written down in this very moment, nor any explicit examples of irrational cubic fourfolds. But I will point you to Tony Pantev's talk from last week. He spoke about forthcoming work due to Katsarkov, Kontsevich, Pantev, and Yu, where they use Hodge atoms as a rationality obstruction for cubic fourfolds and other sort of related varieties. Okay, but then sort of on the other hand, for cubic fourfolds, sometimes we actually get a rationality construction. And that's kind of the example I want to go through right now. So let me make this X a little bit more special. I want to suppose it contains a plane. Even in this case, we still expect the general such one to be geometrically irrational. But since I have this plane, I can do something with it, right? I can project away from it onto a complementary P2. I can resolve this map by blowing up that P2. And this map pi is going to be a quadric surface bundle, right? So if I take a point in P2, I take its span with the plane in X. This gives me a P3 in the ambient P5. It intersects X in a cubic surface, which contains the plane. And so I get this complementary or residual quadric surface, and those are the fibers of the map pi. Okay, and this pi sort of gives me a way to think about rationality, because if pi has a rational section, well, I mean, the generic fiber of pi over the function field of P2 is a quadric surface. And that rational section exactly corresponds to having a K of P2 point on the generic fiber. Okay. And as we just saw, quadric surfaces that have a point are themselves rational. And so having a generic fiber, having a generic fiber here, which is rational over a rational base, implies rationality. And so that tells me that X is rational. Okay, so I want to take another sort of slightly different perspective on this example. I want to think about lines in the fibers of this quadric surface bundle. Okay, so I'll let F1 of pi be the relative Fano variety of lines. All right, so points exactly correspond to lines in the different quadric surfaces here. For most points in P2, I'm going to have a smooth quadric surface. And so I'm going to have two rulings of lines. And those will give me two conics in this relative Fano variety over that point. Okay, and then there's going to be some locus in P2 where the quadric drops rank. And so I get this singular quadric, which then only has one family of lines. And so I just get a single conic corresponding to that point in P2. Okay, so then from this map to P2, I can take the Stein factorization. Right, that's going to map me to this surface S. So the map phi is going to contract connected components of the fibers. And then the second map from S to P2 is going to be a finite map. It turns out in this case, this discriminant curve, the locus where the quadrics drop rank, is a smooth sextic. And this S then is going to be a double cover branched along that sextic. Okay, so what is that telling me? That's telling me that this S is a degree 2 K3 surface, and phi is a smooth conic bundle over it. Okay, well, then if I look now at the generic fiber of phi, so over the function field of S, right, I had a conic, and so geometrically this is actually isomorphic to P1. And so this generic fiber is what's called a very Brauer variety. It's a class, a variety which base changes to be projective space over the algebraic closure. And so those give Brauer classes in the function field of S. Okay, but then actually because this the Severi-Brauer variety sort of came from this family actually over S. That means that this class was unramified, and so actually gives me a Brauer class on the K3 surface. Okay, so where am I going with all of this? I want to sort of rephrase this, this rationality construction in terms of this Brauer class, right? So the Brauer class being trivial meant that that generic fiber was actually P1 over the ground field. And so that corresponds to that conic actually having a point over the function field. And so that point gives me a rational section of this map B. And then the sort of magic here is that a rational section of phi exactly corresponds to a rational section of pi. So let me go back to the picture. So why is that? If I have a rational section of phi, well, let's just think about these smooth fibers. That's saying for each ruling, I'm picking out a point, right? And on one of these smooth fibers, if I pick out a line in each ruling, they meet in a unique point. And so that gives me this section over here of pi. And conversely, if I have a point on the quadric, it lies on a unique line in each ruling, and so it gives this section over here. Okay, great. So, and then as we saw, having a rational section of this quadric surface bundle tells me that the cubic fourfold is rational. Okay, so from my cubic fourfold, I produced this K3 surface and this Brauer class, for which the Brauer class in some sense sort of controls rationality in that if the Brauer class vanishes, then the cubic fourfold is rational. Okay, and this example actually goes back to Brendan Hassett from 1999. He showed that there's a countably infinite union of divisors in C8, parameterizing rational cubic fourfolds. So C8 is the divisor in the moduli of cubic fourfolds of those which contain a plane. And so that's sort of exactly saying this is a locus where you can show that the Brauer class vanishes. Okay, so let me sort of summarize what I just said, and maybe the sort of main point I want to make is that sort of all of this machinery really came from this quadric surface bundle, right? So I sort of didn't need to start with a cubic fourfold. Really, I needed to start with a quadric surface bundle. Okay, so if I take a quadric surface bundle over P2, it has some smooth discriminant curve where the quadrics drop rank. I can look at the relative Fano variety of lines over P2, take its Stein factorization. This is going to give me some intermediate surface, which is a double cover of P2 branched over that discriminant curve. And then the first map is going to be a smooth conic bundle, and so gives a Brauer class on that surface. And if the Brauer class vanishes, then the quadric surface bundle is rational, fourfold. Okay, great. So as I said, so sort of quadric surface bundles are going to be the main player in this talk. But sort of in the title, I said I want to talk about rationality in families, right? So I don't want to just think about rationality, but if I start putting these varieties together in a family, how does the rationality of different how is the rationality of different fibers related? Okay. So let me take X to B to be a smooth projective family. Let me start by working over a field, and let's assume that the base is connected. Then there's sort of different questions that you could ask about this family. Maybe the first thing I should do is point out that I want to assume it's smooth. If I remove this word smooth, then there's sort of basically rationality doesn't have to behave nicely. So for example, if I take I can take a family of cubic surfaces which are rational and they can degenerate to a cone over an elliptic curve, which is irrational. I could take a family of cubic threefolds, which are irrational, and degenerate them to a nodal cubic threefold, which is rational. So I want to sort of assume I'm looking just at smooth families, but then ask kind of the same question. So if I know that a general fiber is rational or irrational, what can I say about a special fiber? And conversely, if I know something about a special fiber, or maybe about a lot of fibers, that they're rational or irrational, what does that tell me about, say, the generic fiber? Okay, so let me go through a little bit of sort of what is known in this setting. And I'm not going to claim to sort of mention all of the results here, but try to give sort of a broad sense of what can be said. So first off, if I work over an algebraically closed field of characteristic 0, Then in low dimensions, so if the fibers have dimension less than or equal to 3, then the locus in the base, which parameterizes rational fibers, is going to be a countable union of closed subsets in that base. In dimension 1, this just follows because the genus is constant in smooth proper families. In dimension 2, it's a consequence of Castelnuovo's rationality criterion. And then in dimension 3, this is a result of Deformation and Fusi. Okay, in fact, sort of in dimensions 1 and 2, rationality is a deformation invariant, by which I mean if you have a special fiber which is rational, then the generic fiber was also rational. Okay, but as the dimension increases, this starts to change. So work of Hassett, Pirutka, and Schinkel shows that in dimension 4, you sort of see something honestly different. They exhibit a family such that a very general fiber is irrational, but then the locus in the base, which parameterizes rational fibers, is dense in the Euclidean topology. And kind of around the same time, Schreider showed that actually you can cook up examples like this in every dimension greater than or equal to 4. Okay, and so you'll sort of notice then I haven't said anything about dimension 3, and this is sort of more recent. So Hassett, Kresch, and Schinkel exhibit a family of threefolds with both stably rational and non-stably rational families. So sort of having an example where you have rational and irrational fibers is sort of, I believe we don't have such an example yet. Is that looking at Brendan for confirmation? Okay. So there's kind of still an open question here about sort of, whether rationality is a deformation invariant in dimension 3, but stable rationality is not. Okay, great. So as I just said, that's saying in dimensions at least 4, rationality is not a deformation invariant of these smooth, complex projective families. And then the last result I want to mention is sort of in the opposite direction. So for any field of characteristic 0, Kontsevich and Schinkel have shown that in every dimension, rationality specializes. So if the generic fiber is rational, then all of the special fibers are rational. Okay, so that was sort of a family over a field. And let me now sort of specialize to what I'm really interested in, which is arithmetic families. So what do I mean by that? I want to start with X, a smooth projective variety over the rationals. Okay, you could replace that with any number field. Then there's going to be some locus B in spec Z, and some smooth projective model over that B of X. So X is the generic fiber, and I mean basically what I'm doing is sort of throwing away all of the primes of bad reduction. So I pick some model and then just keep the smooth fibers. Okay, so now I can ask sort of what is the behavior of rationality in such a family? And very concretely, right, I want to think about if this variety over the rational numbers is rational or irrational, what can I conclude about one of these smooth reductions? Okay, so let me write XP to mean the base change of this model to FP. And conversely, if I know something about some of these fibers, say they're rational or irrational for infinitely many, or maybe a positive proportion, can we conclude anything about X? Okay, and so in low dimensions is kind of the same as before. So dimensions 1 and 2, rationality is again a deformation invariant. So if you have a X sub P, which is rational, then all of the fibers, then the generic, the X over Q had to be rational. And maybe sort of the other results in this direction. So in dimension 3, this is joint work with Lena G. We show that you can have geometrically rational but irrational threefolds over Q, for which the reductions mod P are rational for every prime P of good reduction. Okay, so I think it would be sort of interesting to have an example that's actually, honestly, geometrically irrational. somehow this is really sort of an arithmetic obstruction to rationality for this threefold over Q. But sort of given the state of dimension 3 understanding rationality as a deformation invariant, I think that seems a little bit hard. So, but if anyone has thoughts about how to make such an example, I'd be interested to talk about that. So today I want to focus on dimension 4. And I sort of specifically want to make an example kind of like what I just mentioned, where it's geometrically irrational, but where it has rational reductions for maybe, say, infinitely many primes p. I should pause. Other questions so far? Or?
You gave an example of rational services that try to come over and look at and he said that rationality is also relevant to this. How are these two not in conflict with each other?
In smooth families, rationality specializes. Yeah, the keyword is smooth. Yeah, great. Okay. Okay, so let me sort of revisit cubic fourfolds. Basically, I'm going to tell you there's sort of two ways that I think are sort of natural to try and approach this constructing such a fourfold, and both of them sort of fail in unfortunate ways. So let me take X again to be a smooth cubic fourfold over, now let's just work over Q, and assume it contains a plane. And so I get this associated quadric surface bundle, I get this K3 surface and this Brauer class. And again, these cubic fourfolds are sort of generally expected to be geometrically irrational. And so if I take a prime of good reduction, and let's say, I mean sort of for the cubic fourfold, for the K3, and I want it such that the reduction of the Brauer class is unramified, then basically sort of the entire rationality construction that I discussed earlier goes through in this setting. And so this reduction of the Brauer class being 0 implies that the reduction of the cubic fourfold is rational. Okay, so now sort of asking about rationality of the cubic fourfold mod p can be reinterpreted in terms of this Brauer class becoming trivial mod p. Okay, so how can that happen? Well, let me, if I sort of take the Brauer group using sort of this cohomological interpretation, then I can look at the Kummer exact sequence and take the long exact sequence in cohomology and sort of split off this short exact sequence. Okay. Now I've written everything sort of geometrically, but even using this picture, you can sort of extract information about what's happening over the ground field. So I get geometric Picard group tensor Z mod 2 mapping to H2 with coefficients of mu2 mapping to the 2 torsion of the Brauer group. I mean, I could put any n here. I didn't need to be 2. And then I can do the same for the mod p reduction. By smooth base change theorems, I get an isomorphism in the middle. The Picard group over Q bar injects into that over FP bar. This goes back to work of Malik and Poonen. And I get this surjection on the Brauer groups. Okay, but this is placing a constraint on sort of what can happen for Brauer classes over Q bar versus over FP bar, because if the Picard rank jumps upon reduction, then necessarily this sort of rank of this Brauer group, 2 torsion Brauer group has to go down. So some classes have to vanish. Okay, and so it's really kind of studying this jumping of Picard ranks upon reduction that allows you to say something about Brauer classes vanishing. So this is a result joint with Brennan Hassett and Tony Verrilli Alvarado, where basically we show that sort of in the setting where the Picard rank jumps upon reduction for a positive proportion of primes, then you can also show that any Brauer class is going to vanish for a positive proportion of primes. And so, I mean, there's sort of slightly more general than what I've written, but one assumption you could place is that the geometric Picard rank is odd. And then that's enough to sort of force this jumping. And so maybe I'll mention some of the sort of key ingredients in this proof. We use the Tate conjecture, which has been proved for K3 surfaces, and we use the Mumford-Tate conjecture, also proved for K3 surfaces. Okay, sort of the idea being that we can understand these new algebraic classes mod P by studying Galois representations and allowing P to sort of vary. Okay, and then so maybe if you want sort of weaker conditions on your K3, then this was studied by Malik and Tayu. So again, starting with a K3 over Q and any Brauer class, they still have some technical hypotheses, but they're weaker hypotheses. And then they're able to show that at least at infinitely many primes, you get the Brauer class vanishing. Again, these hypotheses are not too strong. They basically have to avoid a few ranks for the transcendental lattice, and then they need some conditions on the discriminant of the transcendental lattice. Okay, so what's the consequence here, right? This is telling me that if I have one of these cubic fourfolds over Q containing a plane, and I could show that it's irrational, then this tells me that rationality is not a deformation invariant in these arithmetic families of fourfolds. Okay, and again, this if is actually addressed by the work of Panta that I mentioned earlier, so forthcoming. Okay, so you really could use cubic fourfolds to sort of construct one of these interesting arithmetic families, but maybe if we want to sort of avoid this proof of irrationality of cubic fourfolds, it would be nice to have sort of a different construction. Okay, and so, right, I mean, again, the sort of rationality mod P construction really is using this quadric surface bundle structure. So sort of the first next idea would be to try to use some other quadric surface bundle. Okay, so let me consider the following example. So I can take this specific 2-2 divisor in P2 cross P3. F is this specific polynomial. Projection onto the P2 gives this X the structure of a quadric surface bundle over P2. And it has this discriminant curve of degree 8, but it's, it's both it's reducible and not reduced, right? So it's like a very degenerate discriminant curve. But that's actually kind of the point of this example. So this is the example that Hassett, Pirutka, and Schinkel used to construct their family where they have these irrational fibers. Okay, so they sort of degenerate to this setting where they can show that this fourfold has non-trivial unramified cohomology, kind of a Brauer obstruction to rationality. Okay, so you could try to sort of use this X instead. It's certainly defined over Q, and you actually know that it's geometrically irrational. So let me consider sort of more general quadric surface bundles of this form. So let me suppose now I have one with a smooth discriminant curve of degree 8. Then again, I'm sort of back in this setting that we've already discussed. I get this discriminant double cover branched over C, and I get this Brauer class, which if it vanishes, then X is rational. But in this case, now this double cover is branched over this degree 8 curve. So this is an example of a Horikawa surface. Okay, so these are in the classification of surfaces, these are minimal surfaces of general type with geometric genus at least 3 and lying on the Noether line. That's the definition of a Horikawa surface. And so this double cover satisfies that. In some sense, these are like, I think of them as like sort of barely general type surfaces. And so, as I said, the idea now is to sort of construct a fourfold over Q for which at some prime, I reduce to this Hassett-Pirutka-Schinkel example on the previous slide. And so that I could show that this Brauer class vanishes mod P for some, infinitely many primes P. Okay, and right, I sort of mentioned that I want this X mod P to be this Hassett-Pirutka-Schinkel example. In fact, having this X mod P, which is irrational, is enough to tell me that X over Q is geometrically irrational. Okay, so this goes back to, it's called the degeneration method or the specialization method, initiated by Voisin, and then sort of in mixed characteristic, worked out by Alena and Pirutka, and sort of further refined by Schreider. Okay, so having this one fiber that has unramified, non-trivial unramified cohomology implies that the fourfold over Q is geometrically irrational. Okay, and then again, this Brauer class vanishing would give me the rationality mod P. Yeah.
The HPT example, you were taking double cover over use. The user was unused perfect, so the HPT is not smooth surface.
Right. Yeah. So then they basically don't use this discriminant double cover at all. Yeah, they sort of just study the fourfold and its unramified cohomology. Okay, but sort of here's the problem in this setting that sort of all of the tools that we use for Brauer class vanishing on K3 surfaces are just open questions for these Horikawa surfaces. Right? So we don't know the Tate conjecture. We don't know the Mumford-Tate conjecture. I should have mentioned that sort of even in the work of Malik and Taiyu, they use very different methods than us to show this Brauer vanishing, but they still use this idea of Picard rank jumping mod primes. And that's sort of also not understood for these surfaces. So, okay, so I think, this would be another way to construct one of these examples. If somebody could prove the Tate conjecture for these surfaces, that would be sort of a big first step in that direction. Okay, so those are kind of the two, I think, like first attempts at constructing such a family, and they both fail in different ways, right? In one case, we sort of don't yet have the proof of irrationality, and in the other case, we can't actually prove rationality mod P. Okay, so that brings me to the main result, again, joint with Auel and Alena Pirutka. So we show that indeed rationality is not a deformation invariant in these arithmetic families of fourfolds. And we do that by constructing one of these fourfolds over Q, which is geometrically irrational and which has xp rational for some positive proportion of primes P. Okay, and we sort of don't prove the Tate conjecture for any surfaces, unfortunately. That would be great, but so the proof is sort of to combine these two examples that I already discussed. So on one hand, we're going to use a reference variety very similar to this Hasse-Pirutka-Schinkel example to get the geometric irrationality. But then we're going to relate this fourfold to a quadric surface bundle, which has an associated cubic fourfold and thus an associated K3 surface, and we can use those Brauer class vanishing results for K3 surfaces. Okay, so let me now go through the construction. I'll try to say a few things about sort of how you construct these quadric surface bundles generally, and what our specific family looks like. So in general, to make a quadric surface bundle, you want to construct it sitting inside the projectivization of some vector bundle on the base. And so I'm going to take this rank 4 vector bundle, O of 1 plus O plus O plus O of minus 2. And the quadric surface bundle is determined by this morphism from the symmetric product of that line bundle, of that vector bundle mapping to a line bundle, and I'm going to take O of 2 here. Okay, so we call this a quadratic form valued in the line bundle L. And so you can look at the Gram matrix for that quadratic form, and this sort of determines your quadric surface bundle. Okay, so I'm going to take sort of this special symmetric family where the Gram matrix has, what's the key thing to notice here? X and Y always show up with even degree. And then sort of for most terms, Z also shows up with even degree, but I have these like linear Z terms here. Okay, so the L's are linear, the Q's are quadric, the C is degree 3. And so sort of on the diagonal, I have degree 0, degree 2, degree 2, and degree 6. Okay, and so then when I make this quadric surface bundle, it's going to have discriminant curve exactly given by the determinant of this matrix. And so as I just said, this 6 plus 2 plus 2 plus 0 is 10. So this is going to have discriminant curve in P2 of degree 10. And as I mentioned, the key is that that this matrix and thus the the quadratic surface bundle is invariant under the involution sending x to minus x and y to minus y. And so what I can do is quotient by this z mod 2 cross z mod 2 action. Okay, so I get this diagram. I'm going to sort of keep adding to this diagram, so bear with me. Eventually, the point of this diagram will become clear. So I have my quadratic surface bundle that I started with, my curve C of degree 10. And Q is going to be my quotient map. Of course, I sort of mentioned I get the map on the fourfolds, but of course, I get this map from P2 mapping to weighted projective space. I'll write it 2, 2, 1, just so we remember that it's the x and the y that are now weighted degree 2. And so I get this quadratic surface bundle over this weighted projective space. And then this weighted projective space is actually isomorphic to P2. Okay, as a coarse space, if you're worried about the stack structure, then they're not going to be the same stack, but just sort of underlying varieties, they're isomorphic. And this isomorphism basically is given by sending z to z squared and then sort of dividing all of the weights by 2. And so sort of doing that division by 2, I really need to here sort of start with even degree information. And I'll maybe just go back and remind you that my E has this term O of 1 in it. Okay, so the sort of magic here is that on this weighted projective space, O of 1 is actually isomorphic to O. And so under this isomorphism and along with the isomorphism to P2, sort of I get a quadratic surface bundle over P2. But now my discriminant curve has degree 6. Okay. So I mean, maybe what you would have expected was I started with degree 10 here and so weighted degree 10 here. And so when I sort of divide degrees by 2, I get degree 5. And that does happen. My discriminant curve has 2 components. It has a quintic, and I pick up a line under this isomorphism. Okay, so then I can also consider these discriminant double covers, right? For my original quadratic surface bundle, I have this surface T, which is a double cover branched along this degree 10 curve. This is another Horikawa surface. And I get some Brauer class on that, which if it vanishes, then my y is rational. And then I get a discriminant double cover for my new quadratic surface bundle x prime to P2. And this is now branched over this singular sextic curve. So this is a singular K3 surface. Okay, in fact, this is one of the famous 95 K3 surfaces that have originally studied by Reed and later by Yonemura. So these are 95 families of K3 weighted projective hypersurfaces. Okay, so this K3 actually can be realized as sitting inside weighted projective space P5221. And then the double cover is given by sort of forgetting the first component. So actually, there's a lot of really sort of interesting families in this list of 95, and you could try to do this construction for one of these other families. There's a lot of other of these singular K3 surfaces that are double covers of some weighted projective space like this, and you could sort of try to construct such a picture in that way. Okay, and so along with this singular K3 surface, I get a Brauer class, but again, now it's only in the Brauer group of the function field. It's because I have these singular points, the class doesn't have to be unramified. Okay, but I can resolve singularities to get an honest K3 surface. And you can check that when you pull back the Brauer class under this resolution of singularities, it really is unramified on the smooth K3 surface. Okay, so I get an honest Brauer class in the Brauer group of S when I pull it back. Okay, and then the quotient map T also induces a map on these discriminant double covers. And so under this map that I called Q prime, right, I can take my Brauer class alpha and pull it back, and it exactly pulls back to the class beta that we get here. Okay, so as I said, I am going to get this very complicated picture. So what's the point? Why did I do all of this? So here's the upshot, right? If I have a prime of good reduction, and sort of everywhere that it makes sense to have a prime of good reduction, let me assume that, then if the Brauer class back here on the K3 vanishes, then then when I pull it back to T, it had to vanish. And so that tells me for those primes that my reduction of Y mod P has to be rational. Okay, and on the other hand, if we can construct one of these Y's so that at some other prime, this reduction has non-trivial unramified cohomology, then again, using this degeneration method, we get that Y is geometrically irrational. Great. Okay, so questions about the setup or construction? Okay. Okay, so I guess maybe I should say it's sort of not so hard to prescribe sort of that one of the reductions look a certain way and construct a reference variety where you can sort of use the same techniques from the example of Hassett, Pirutka, and Schinkel to kind of show that there's non-trivial unramified cohomology. So kind of really the real work is in constructing this Y so that this K3 surface S satisfies the conditions for Brauer vanishing. And so I'll just remind you what those are. So if I can make my S have geometric Picard rank odd, then I get the vanishing for a positive proportion of primes. And well, maybe if I don't have Picard rank odd, I could still satisfy these technical hypotheses and at least get infinitely many primes where I have vanishing. Okay, and the issue is that sort of given the family that I wrote down on the previous slide, it's not going to satisfy either of these conditions. Okay, so right, again, to get this S, I had to resolve the 5 points where the quintic meets the line. And so that's going to take sort of generic rank 1 up to rank 6. Okay, so a general one here should have Picard rank 6. And then the technical hypotheses that I didn't exactly tell you, sort of one of them is that the discriminant of the transcendental lattice needs to be co-prime to the order of the Brauer class. But ours has the Brauer class is order 2, and the discriminant is a power of 2. Okay, so the fix is really to just sort of take this construction and specialize it in such a way that that I get my K3 having odd Picard rank. Okay, so what we do is take our Y so that this resulting quadric surface bundle X prime to P2 has still this quintic and this line, but now the quintic is nodal. And so to get the smooth K3 surface, I have to blow up one more point, and so I should have Picard rank at least 7. And so sort of the final step is to show that you have an example with honest geometric Picard rank 7. Okay, so let me just sort of summarize that again. Right, we produce this quadric surface bundle over P2 so that this resulting K3 surface sort of on the other side has Picard rank exactly 7. And so the Brauer class vanishes mod P for some positive proportion of primes. And so the reduction of the fourfold mod P is going to be rational for all of those primes. And then there's some other prime P prime for which the reduction has non-trivial unramified cohomology. And so that fiber is irrational, and also the total space is geometrically irrational. Okay, great. I have a little bit more time still. So let me sort of the last thing, if I had time, that I wanted to say was, like, in general, calculating geometric Picard rank of a K3 surface is not so easy. So how do we get an example where we can say for sure that it has geometric Picard rank 7? Okay. So let's see. As I mentioned, my S is this resolution of S prime to P2, where it's double cover branched over this sextic. The quintic component is nodal, and I want to assume that Q and L meet transversely in 5 points. And so when I sort of blow up all of those things to get something smooth, I have Picard rank at least 7. And so now to sort of control Picard rank, I want to start looking at reductions mod P. Okay? So as I mentioned, you always have this inclusion of the geometric Picard group over Q mapping to that over FP bar. And so, like, if you had some prime where the Picard rank was 7, then you would sort of win. But the issue is that the Tate conjecture for K3s implies that mod P, the geometric Picard rank, is always even. So kind of at best, you could bound it by 8. And so really sort of you need some extra work to differentiate these things being rank 8 and this thing being rank 7. Okay, and so what we do is follow sort of this idea of Van Lauk, where we sort of look at two different primes and compare the behavior. So our first prime, we look mod 7, and we can show that we have mod 7 geometric Picard rank 8. And in particular, we want to sort of be able to say something about the discriminant of this Picard lattice. Right? And so for this specific prime, we show that sort of this extra generator is given by a tangent conic. So it's tangent to that discriminant curve. And so in the double cover, it splits and gives an extra class. And so then because we understand all of these curves, we can just write down their intersection lattice and get the discriminant. It's negative 128. And so then the Picard lattice is going to be some overlattice of that. And so it'll have discriminant, a divisor of 128 differing by a square. Okay, so in particular, it has to be a power of 2. And then we look at mod a different prime. So it turns out 73 is sort of the prime that works well for us. Because over this prime, we again have geometric Picard rank 8, but actually all of those classes are defined over the ground field. So honest Picard rank 8. And now we can use the Art and Tate formula. I mean, maybe I'll mention sort of the classical technique here would be to like find some other prime where I also explicitly understand the extra curve class and can sort of in the same way compute the discriminant. But because our sextant curve is degenerate in this way, it's like very difficult to get our hands on some other sort of prime where we actually understand the extra class. So the Art and Tate formula is a way to get around that. It sort of relates the discriminant and the order of the Brauer group to approximately sort of evaluating the Weil polynomial at the prime. And so this formula tells us that both 5 and 37 have to divide the discriminant mod that prime. Okay, and so then the contradiction here is that if I had geometric Picard rank 8 over Q, then this inclusion would be as a full rank sublattice. And so the discriminant over Q bar would have to, up to squares, be equal to both of the discriminants, mod 7 and 73, and that just can't happen. So, great.
5 and 37 divide, they divide to an odd power.
Yes, thank you. Yes, exactly 5 and 37 to 1 power divide the discriminant, actually. Yeah, thanks. I should have said, yeah, up to squares. Yeah. Great, so that's sort of, that's how we get that sort of last ingredient of really identifying the behavior of this K3 surface. So I will stop there. Thanks.
There are any questions? Thank you for the next one. So, what is not about this rationality in smooth families over some other non-algebraic things?
That is a great question. To which I am not totally sure, actually. Yeah. My impression is that there's not so much known in non-algebraically closed field cases, but yeah.
What kinds of American stuff, similar to success plan?
They're all like simple nodal, yeah.
Sorry, so can you go back like maybe the last slide of the diagram?
Yes. Here.
Okay, right, I think so, maybe not this slide, but I think maybe there was something I misunderstood, like something like all parts of the reduction. Something, maybe it's a few slides back. Sorry.
That's okay. Here?
Yes. Okay, thanks. Sorry, now I understand.
Okay,
thanks.
Yep.
So, can I ask the question?
Yes.
So you notice there's a positive proportion of times for which it's rational, and you know that there's at least one time for which it's irrational.
Mhm.
Do you expect there to be a positive proportion for which it's also irrational?
That's a great question. My feeling is yes, but I don't have any real reason for that, I guess. Yeah, so maybe I should say I don't know.
Oh, I just have a comment that's kind of tangential to this, but about some things you were saying at the beginning. You mentioned that, that degeneration of a rational, in characteristic zero, that degeneration of a rational variety is also irrational. And so I think that will imply formally that if you have a family, then the locus on the base where the fiber is rational should always be countable union of flows. Right?
Oh, in every dimension.
Yeah, in every dimension.
Yes,
Yeah, you mentioned that was known in dimension 1, 2, 3.
yes, yeah, you're right. Yeah, thanks for pointing that out.
Yeah, that's
Great,
stop.
thanks.
I have one related to this question. Like, do you know anything about the Brauer class? Like, does that vanish? Like, does that the non-zero for positive portion? I know the converse is not true, but it's not zero.
I also don't know the answer to that. Yeah. Yeah, I'd have to think about it a little bit more. Yeah.
The other. No, this time Sarah again.